Okay, everyone, here in chapter 24, we're going to look at what is a very common and popular statistical inference procedure called one-way analysis of variance, or ANOVA for short. ANOVA is used primarily for comparing multiple sample means to one another. When I say multiple, I mean more than two, all right? So you'll recall that when we talked about t-tests, we looked at a two-sample t-test, and in that case, we were comparing the means of two separate and independent samples to each other. And effectively what we were doing was looking to see through the two-sample t-test if those two samples had been collected from the same population or from different populations. If we found a statistically significant difference between them through the two-sample t-test, then the inference was that they came from separate populations regarding whatever it was we were measuring. If we found no statistically significant difference, then they were assumed to have come from the same population. We also talked about, during that chapter on two-sample t-tests, the problem of multiple comparisons. Remember, we said that for any single comparison between any two sample means, we accept a 5% chance, typically alpha 0.05, so we accept a 5% chance of making a type 1 error. But every time you do a comparison like that, you have the same chance of making a type 1 error. So the more comparisons you make, the more likely it is that you will eventually make a type 1 error. If you do 100 different comparisons, on average, statistically, you can expect to make 5 type 1 errors. And so the more you do it, the more comparisons you make, the more likely it is you will actually make an error. So as a result of that, we can't compare more than two means to each other through separate two-sample tests. For example, we couldn't compare mean A to mean B, and then mean A to mean C, and then mean B to mean C. That would be 3 separate comparisons, and we have a 15% chance of creating a actually having a type 1 error, and that's just not acceptable. The ANOVA test, or what's called the one-way ANOVA, is a way to get around that. It's a way to look at multiple sample means, again 3 or more, and look for any overall statistical significance between them without encountering that multiple comparisons problem. Okay, so here again with the one-way analysis of variance, we're going to compare multiple means to one another. And technically, the test is referred to as the ANOVA F test. And as with all of the inference tests that we've looked at, there are certain assumptions that our data have to meet. Once we get through all that, then probably in the second chapter, we'll deal with the ANOVA calculations, how to use a new table called the F table, and then finally how to interpret the results of the ANOVA. Okay? All right, so let's look at an example here. As I've already said, when we're comparing more than two populations, we have to avoid that problem of multiple comparisons. And so the question in a situation like this is not only whether each individual population mean is different from the others, but in other words, whether or not we have multiple populations that we're sampling from, but also whether they are significantly different when taken as a group, when considered as a whole. So as an example, let's say we split a class of 200 into 20 random samples of 10 students each, and we found the mean heights of those 20 different samples. If you look at those, you're going to see that one of them will be the smallest mean value and one the largest. So if you take those two most extreme samples and do a two-sample t-test between them, they very likely might be significantly different from each other. Okay, but that could be a type 1 error. There's always a 5% chance of that if we set our alpha at 0.05. The better question to ask when we have multiple samples to compare is if all 20 of these samples might have come from a single population or not. And that is, in effect, what the analysis variance test is asking. Okay, you have multiple different samples. The test is asking, might it be that these all came from the same population? All right, let's look at some examples here. So let's say we have a population, so circled here in blue, right? And we take multiple different samples from that population. okay? Let's say we compare samples 3 and 5. So along the x-axis, whatever it is we're measuring here, they are the two most extreme. Sample 3 has the lowest average along that axis. Sample 5 has the largest average along that axis. We compare those two directly with the two-sample t-test. It might well be that they are significantly different from each other. Now, let's say we compare sample 3 and sample 2. Maybe they're not far enough apart to exclude the possibility that this difference here is due just to random variation, and so maybe we don't get a significant p-value. Maybe we don't see that they're different through a two-sample t-test. We compare sample 2 and sample 5, maybe the same thing. Maybe we find that they are not statistically significantly different. So the question is, if sample 3 and sample 5 are significantly different, but sample 3 and sample 2 are not, and sample 2 and sample 5 are not, what is going on here with our assumption, with our inference that sample 3 and sample 5 are significantly different? To put it in more general terms, if A equals B and B equals C, does A equal C? If sample 3 equals sample 2 and sample 2 equals sample 5, does sample 3 equal sample 5? So this is one of the problems that we have to deal with or consider when we're looking at comparisons of more than two sample averages. All right, for example, maybe this is the case, right? Maybe samples 3 and 2, along with the others, are part of population A, but maybe sample 5 is part of a separate population altogether. So with analysis of variance, there should only be a single null hypothesis, and it should state that we have sampled many times from the same population. It'd be wrong, as I said, to test a series of two-sample null hypotheses or to only test the two most extreme results. If you test only the two most extreme, you're not considering all the other samples, obviously. If we set our alpha at 5% and run, again, multiple analyses, say a two-sample t-test between 3 and 2, and 2 and 6, and 6 and 4, and 1 and 4, and do all possible comparisons here, we are dramatically increasing our risk of making a type 1 error, and that's not acceptable. All right, another possibility. Maybe this is the situation, right? Maybe sample 3 rather is from population C, sample 5 is from population B, all the other samples are from population A. We don't know what the case is here, but the analysis of variance is basically going to look at all these different sample averages and help us figure out if this is the case, if that's the case, or if that's the case. This is what analysis of variance does. Okay, so first thing we have to do when looking at multiple samples through statistical inference is to look for an overall statistical significance, all right? In other words, we're looking to see if among all possible comparisons of these samples, if there's even one difference among those sample averages, okay? Is there any difference, any statistically significant difference anywhere in all the possible comparisons of these samples? And again, that's what the ANOVA F test is going to do here. So if we do the ANOVA F test and we get a significant p-value, all that tells us is that somewhere in all possible comparisons of those samples, there's at least one significant difference. It doesn't tell us where it is. It doesn't tell us which comparison or comparisons in particular we find a significant difference. It just says somewhere in all that those possible comparisons, there is at least one significant difference. That's what chapter 24 here is about. Subsequent chapters, I think 25 and 26, actually go into more detail on what are called follow-up analyses that can pinpoint those differences very precisely. But as we're going to see in the second half of this chapter, we can use some graphs to kind of figure out on our own in a less rigorous way where those differences might lie if we do find any, okay? But the other methods are a little bit beyond the scope of this class, so we're not going to go into those this semester. All right, before we get into the mechanics of the ANOVA F test, we need to go back and sort of revisit variance and standard deviation, because the ANOVA F test is based on these two statistics, these two measures of variation, all right? Remember, variance and standard deviation are a way to measure variation around a mean or an average. All right, now I gotta fill these in here real quick. Okay, so remember the variance is S squared, all right? And, whoops, sorry, go back. And what the variance is doing is looking at the deviation of each individual data point or sample from that sample mean. So, for example, over here we have a sample mean. So the sample mean is in red, the individual data points in that sample are in blue, but this is the average. And so for this data point, you subtract the mean from it and you get its deviation right there. For this data point, this is the deviation from the mean, and so on, right? So we have all these different deviations from the mean. For variance, we take each individual data point, subtract the mean from it, we get its deviation, and we square that. We do this same thing for all the rest of the measurements, the data points in the sample, then we add up all those square deviations. All right, this is what's referred to as sum of squares. The sum of squares is a very common measure of variation that you see in a lot of statistical analyses, and we see it for the first time really here pointed out specifically in the ANOVA F-test, okay? Now, we take that sum of squares and then we divide it by our degrees of freedom, which in this case is n minus 1. That's our variance, s squared. Now, to find the standard deviation, you'd simply take the square root, right? So standard deviation is s, it's the square root of the variance, the square root of s squared, which again is this. So all we've done is calculate the sample variance, then convert it to a standard deviation by taking the square root of that variance number. The sample variance very often is a very large number because, again, you're squaring, right? So converting it to standard deviation is putting it back into a number more along the lines of the units of our measurement, whatever it is we're measuring. So standard deviation is more intuitive, but a lot of times you see sample variance being used as well. Okay, so again, our question here that we have with ANOVA is, are the observed differences in sample means likely to have occurred by chance just because of random sampling? That's always the question we're looking at really in any sort of statistical inference, whether it's a z-test or a t-test or a chi-square test, or here with ANOVA, okay? So let's assume we've sampled several times from the same population, okay? And the population has some mean that we're trying to estimate and some standard deviation, but we don't know what either one of those are, all right? Well, let's say we have 3 different samples from that population, and so those sample means are indicated here by these green asterisks. So we have some x-axis of whatever we're measuring. First sample falls at about 23.5, let's say. Next one about 25, and the third one about 27.5, let's say. These are the means of our 3 samples. All right. This sample mean, this first one here, is calculated from this set of data. These 5 data points, if you average them, give you that sample mean. These 5 data points give you that sample mean, and these 5 data points give you that sample mean. So we have 3 means, we have our 1, 2, 3 samples that those means are calculated from. All right, now, what ANOVA is really doing is it's comparing 2 different sources of variation to one another. It's looking at the ratio of variation from 2 different sources, okay? It's looking at the ratio of variance between sample means to the ratio of variance within sample means. So between sample variance to within sample variance, all right? That's what's going on here. Okay, if it turns out that we have more variance within our samples, right? They're widely spread along some x-axis, and we have lots of overlap between the samples, as you see here, right? Lots of overlap between them along this x-axis. If you have more variance within your samples than between your sample means, that's an indication that all 3 of those samples, or those samples, came from the same population, and that the variation we see in the sample averages is just random variation, all right? Okay, on the other hand, if we have a situation where, again, we have the same 3 sample means, but now they're calculated from these different samples, Notice that in these samples, the data points are much closer together. They're not nearly as far spread apart along the x-axis as they were in the previous slide. So here, these 5 very closely spaced measurements give you that average, these 5 give you that, and these 5 closely spaced measurements give you that. Here, we have a situation where if you calculate the variance of these 3 averages, in other words, you calculate the average of these 3 and get what's called the grand mean, then subtract the grand mean from each of these to calculate your variance, you have more variation along the x-axis between your sample means than you do within any one of your samples. Here, there's not much variance at all, not much variance there, not much there. There's more variance between your samples than within. In this case, that's good evidence, there may be good evidence that these 3 samples come from different populations. I mean, look, there's no overlap between them really in terms of their actual values of data points, suggesting that they probably come from different populations. That is not the case in the previous example. There's so much overlap between these, it's easy to imagine that the variation we see here is just random sampling variation, and that these 3 sample means represent measurements from the same population. Whereas in this case, those 3 sample means probably represent samples from different populations. So when we have more variation between our samples than within, that's an indication that the samples may have come from a different population. And so the ANOVA F-test is going to look at the ratio of between sample variance to within sample variance, right? And that ratio is called the F statistic. So again, with statistical inference, we're calculating a statistic. In this case, it's called the F statistic. We did it before with the T statistic, chi-square statistic, the Z-score. But in every case, we're going to look up that value on a statistical table, and that will help us find the corresponding p-value, which then will help us to decide to either accept or reject our null hypothesis. Okay, so let's assume you've measured flower lengths for 3 different populations of flowering plants, and we need to test the null hypothesis that the mean lengths, the hypothesis that the mean lengths are different due to some biological effect rather than just through random sampling error, okay? We know that we can't perform 3 separate t-tests because of the multiple comparisons problem. That would give us a 15% chance of making a type 1 error, all right? That's the problem there. For example, like I said before, if we perform multiple comparisons, multiple 2-sample t-tests, 100 comparisons will result in an expectation of 5 type 1 errors. So you're going to get type 1 errors if you do that, right? Can't do that. So we're going to do the ANOVA. But in addition to that multiple comparisons problem, multiple p-values that you would get by doing multiple 2-sample t-tests don't give us any indication of how likely it is that multiple sample means are spread apart as far as ours are. It doesn't tell us how likely it is that our sample means are spread apart as far as they are if our null hypothesis is true, okay? For example, maybe 2 mean flower lengths of 34.6 and 49.2 millimeters are significantly different. But if you consider the third sample, maybe it falls smack in the middle of these 2 values, and it may be that 34.6 and 49.2 are really just extremes of continuum of flower lengths. In other words, the flowers come from the same population with regard to the same population distribution with regard to flower length. This is the problem of multiple comparisons, all right? And it's the problem that ANOVA helps us to get around. So let's look at an example here. So male lab rats were randomly assigned to 3 groups differing in access to food for 40 days. The rats were weighed in grams at the end. So group 1 had access to, rat chow only. Group 2, chow plus access to cafeteria food restricted to 1 hour every day. Group 3, chow plus extended access to cafeteria food all day, every day. Cafeteria food was bacon, sausage, cheesecake, pound cake, frosting, and chocolate. All right, the question here is, does the type of food access influence the body weight of male lab rats significantly? Well, I mean, it seems sort of obvious that the group 3 rats are probably, if anybody's going to gain weight, it's going to be the group 3 rats, certainly. But again, we have to test this statistically, right, objectively. So our null hypothesis here is simply that the means of the three groups, the mean weight gain of the three groups, is going to be the same. So with ANOVA, your null hypotheses are very straightforward. It just says that the means of all the groups are the same. The means of all the populations that you're sampling from are the same. If that's true, then there is only one population, right? If the means of all three populations are the same, they are one and the same population. The alternative here under ANOVA, the alternative hypothesis, is simply that the null is not true. In other words, at least one population mean is different from all the others. At least one. Could be more, but we don't know for sure. All right, so if we plot our rat weight gain data here, we can see that on the chow group down here, we have these data points. So what we have 19 data points right there, and the red point is the average. For restricted, we have 16 data points, the red's the average. For extended, we have 15 data points, and the red dot is the average, okay? So if you look at the averages, it does seem to be arcing upward, which is what you'd expect. But our question is the differences that we're seeing here in weight gain between these three means, is that difference great enough to exclude the possibility that this is just random sampling variability? You know, maybe if our null is true, you do this test again and you don't find that upward curving pattern. Maybe they all line on a parallel line, or maybe one, the restricted or extended is lower than the chow. Who knows, right? But that would be a case of just random variation coming into play. We want to see if this is a real biological effect of different diet. That's what we want to see. All right. So, some reminders here. A factor is a variable that can take one of several levels that we use to differentiate one group from another. All right. In our rat weight gain study, we had one factor, and that was diet, and we had several different treatment levels: chow, restricted, and extended. So our factor was diet with 3 different levels, okay? When in analysis of variance, when you have only a single variable, only a single factor that's split into multiple different levels, then that is referred to as a one-way ANOVA, a one-way analysis of variance. It's also called a completely randomized design, but more often than not, you hear it as a one-way ANOVA, okay? Now, that's what we're doing here in chapter 24. So this is the one we're dealing with now, right? 3 groups of rats exposed to 3 separate diets. But what if, in addition to the kind of diet that they were exposed to, we also divided the rats out by sex. So we put them into male and female groups. Well, then you have 2 different factors or variables. One is diet with 3 levels, restricted, chow, restricted, and extended, and the other is sex, male and female. So now you have 2 variables with multiple levels of each. That is referred to as a 2-way or a 2-factor analysis of variance. Okay, and it's much more complicated in the analysis, and that's something that we're not going to deal with in this chapter or this course. All right, we're looking only at one-way ANOVA, and that is used for what we call completely randomized one-way designs, which is what the rat example is. Okay, so let's look at the ANOVA F test here. So the analysis of variance F test is going to compare, as I said, variation due to specific sources, levels of the factor, with the variation among individuals who should be similar. So again, we're looking at variation between sample means and comparing that to variation within the samples themselves, all right? And again, our null hypothesis is that all the population means are equal, which is just a fancy way of saying that we have all of our samples came from one population. And the alternative is that not all population means are equal. In other words, that our null is not true. So our F statistic, as I said, compares variation among the sample means, this is between sample variation, to variation among individuals in the set of samples. This is within sample variation. So here for this denominator, we basically take the variance of each of the samples and add it all up. and that gives us one number for our denominator. All right, we're going to divide the numerator variance, the between sample variance, by the within sample variance, and that gives us a value of f. Okay, so let's look at this again. So first of all, some terminology, okay? Our F statistic, as I said, is variation among sample means divided by variation among the individuals within the samples. The numerator, variation among sample means, referred to as MSG, or mean square for groups. Mean square for groups. You may see that on an ANOVA output table for Minitab or some other program or whatever. The denominator, the within sample variation, is the mean square for error, MSE. All right, so just think of this, MSG, the numerator, as variation between your sample means, and MSE, the denominator, as variation within the sample means. All right? Okay, so on this example here, notice the color coding, right? Blue, the blue text in A refers to this set of samples. The red text in B refers to this set of samples. We're comparing both to our between sample mean variation. So we get these three sample means from this data set and also from this data set, all right? Now, again, in this data set, look at how much spread there is within a given sample. A lot of spread along this x-axis, whatever that axis is measuring. A lot of spread here for sample B, a lot of spread there for sample C, all right? Now, if you take these three sample averages, add them up and divide by 3, you get the grand mean, the mean of these three means. Then you subtract that mean from each of these to calculate the variance between our sample means. You compare that variance to the total variance in these three samples, the within sample variance, and you have more variance here. And you can tell that by looking at it because there's much more variation along the x-axis here than between the sample means. So, if you divide a small number by a large number, you get a small number. Think of dividing 1 by 4, you get 0.25. Divide a small number by a large number, you get a number less than 1, or a fraction. All right? Now, let's assume this is the case. You take the variance of this sample, the variance of that one, and the variance of that one, and sum it. Total it all up. You get your within sample variation. Here, less variation in each along the x-axis. Maybe you have more variation between your sample means along the x-axis. So in this case, divide a large number by a large variance by a small variance, and you get a large number. For example, divide 4, let's say, by 1, and you get 4. All right, so in the first example with the blue here, variability of means smaller than variability within samples, your F tends to be small. And as with any test statistic, the smaller the value of it, the larger your p-value, and the less likely it is to be statistically significant. In this example, variability of means is larger than the variability within the samples. F tends to be large, and so this would tend to give you a small p-value, which is more likely to be significant. Okay? All right. Let's look at some assumptions. So as with any test of statistical inference, there are certain assumptions that our data has to meet. So first of all, for ANOVA, the samples, the K samples, however many samples we have to be independent random samples. That means that, for example, with the rats study, the rats had to have been placed into each of those three diet categories totally at random. That's what that means. They're totally independent. There's no bias going on in terms of which rats go into what group or what diet group, that sort of thing. Secondly, each population represented by the number of samples, the individual samples, must be normally distributed. All right. If they're not normally distributed, however, as long as our total sample size, the total number of measurements across all of our samples we're considering is large enough, then we can get around this problem, okay? And that's because the ANOVA test, like the t-test, is fairly robust to deviations from normality, skew, mild outliers, that kind of thing. So as long as we have a large enough number of measurements totaled across all of our samples, then because of the central limit theorem, we can, a little bit of skew or non-normality, mild outliers is fine. Usually you probably want to have a total sample number of about 40 or so if you're concerned about this, okay? All right. Third, the ANOVA F-test requires that all populations have the same standard deviation. Now, there are tests for this where you can actually get a p-value to determine if the standard deviations that you're looking at across multiple samples are the same, but they're problematic. They can be sensitive to deviations from normality, and there are other issues as well. So generally, the most conservative approach is a simple rule of thumb here, all right? And that is that the ANOVA F-test is approximately correct when the largest sample standard deviation is no more than twice as large as the smallest sample standard deviation. So you do, you have, say, 3 samples, and you plug those samples into Minitab, and you tell Minitab to do or to spit out descriptive statistics, and you include in that standard deviation. You look at the standard deviations. If the largest one is more than twice the value of the smallest one, you can't do the ANOVA, all right? You have to hang it up, maybe collect more data or do a redesign or whatever. But if your data pass that test, you can go ahead and do the ANOVA. And also, an important point, having equal sample sizes in each of your samples, say 20 rats, 20 rats, 20 rats in 3 different diet groups, that makes the ANOVA even more robust to deviations from the equal standard deviation rule, okay? And it's always a good idea to try and get equal sample sizes, although life happens and sometimes it's just not possible. All right, let's go back and look at our rat example again. So again, we have these 3 groups of rats that were subjected to different diets and weighed at the end to see what their weight gain was. So first question, do we have independent random samples? Well, it says they were randomly assigned to 3 groups, so yes, we're okay there. Normal populations or large enough samples. Well, if you look over here at the individual value plot, you may have, 1 outlier there, but this seems normally distributed with no major outliers for the most part here, and that's okay as well. But also, we have a total of, 50, I think, in terms of sample size, roughly. So we're okay. Okay, as long as we're over 40, we're probably good. So this small potential outlier here is not going to be a problem. So we're okay on this one. Oops. We're okay on that one. Now, what about equal population standard deviations? Well, take a look at your summary data down here. Your smallest standard deviation is 49.64. Your largest is 63.41. This number is not twice that number, so we're okay. We can do the ANOVA F-test on this data, no problem. All right, let's look at an example that doesn't fit the assumptions of ANOVA. Meconium is a newborn baby's first stool, indicative of the fetus's exposure to outside contaminants during pregnancy. The question is, do cigarette chemicals reach the fetus in the womb, let's say if the mother smokes? Cotinine is a metabolized form of nicotine. Its presence in the meconium was assessed for 3 independent random samples of newborns with different mother smoking status. So we have active smokers, non-smokers, passive smokers. These are the smoking status of the mother. And so we see our means here, right? Well, it certainly looks like the pattern we expect. Non-smokers have the lowest cotinine levels. Passive smokers, those exposed to secondary smoke, have the intermediate level, and then the highest level of cotinine is in active smokers. But look at our standard deviations. The largest is certainly more than twice the smallest. Okay, it's about 6 times. So we can't do an ANOVA on this. Look at the individual value plot, and you see the problem right there. Right, there's just so much variation in the active smokers group. Maybe if we go back and remove that one as an outlier, if you can justify that, that might make this better. Maybe you collect more data over here and get a few more data points in this group up here. That might even it out. But as it is, with these standard deviations, we cannot do this test. Okay, ANOVA just is not appropriate in this example. All right, so the next thing we're going to get into is the ANOVA calculations, and I think we're going to leave that for the second video to finish